Hey science family, we are going to start a new unit, and to start it we're going to focus on Newton's three laws, which are super important for describing the way the world works and moves, and then also something momentum today. So let's get into it first with Newton's first law. If you take a look at this picture though, think about what exactly happened here. This right here looks like limestone or some very heavy rock material. And all of a sudden, it slammed through the front of the truck and crushed the front. And then in letters here, it says inertia. A truck has brakes, the massive hunk of stone doesn't. So inertia is the idea of maybe if an object is moving, it wants to keep moving. And that overlaps very much so with what we call Newton's first law. So let's get into it. A little background information before we could get into Newton's law. Galileo, a famous scientist, figured out that an object really doesn't need to be pushed by something over and over again to keep it moving. In fact, we were learning that an object will continue to move unless some kind of force is acting against it. So let's get into that, but first define a couple things. Remember, a force on an object is just pushing or pulling. And don't forget about friction, something we haven't officially defined, but that shows up in our lives constantly. And that's the force between two materials whenever they're touching and if they're moving past each other. There's that force that resists the motion, right? Like friction allows us to stand up and walk around instead of sliding all over the place. It was observed, though, that if you had a ball and rolled it down a ramp, it would technically keep going on and on forever unless friction was working against it. And honestly, that's the reason why we have to keep pushing things to keep them moving, is because friction slows them down. Now, if it's a ball, it could be the friction between the ground and the ball, but also don't forget about the air. The fact that the ball is moving through the air would work against it as it rolls, and that would be a type of friction as well. But we did observe that if friction could be eliminated, this ball would roll on and on and on forever. This related to what is now called Newton's first law of inertia. All right, and what that means is if an object is resting, it usually continues to rest unless something works against it to move it. So an object at rest wants to stay at rest, or an object that's moving wants to keep on moving at the very same speed and in the same direction unless there's an unbalanced force. So if you have a rock on the ground and it's sitting there, it's not going to move unless someone pushes it, right? That would be considered an unbalanced force. And again, going back, if we have like the idea of a basketball and it's rolling on the ground, it will want to continue rolling at the same speed and in the very same direction unless there's that unbalanced force. And we know often that that unbalanced force is what we call friction. But Newton's law states that an object that isn't moving really isn't going to start moving unless there's an unbalanced force. And an object that already is moving will want to continue to do that unless an outside unbalanced force acts against it. So some big important questions of why this is true. All right, well, whatever state an object is in, it is resisting changes to that state of motion. What does that mean? It means if the object's moving, it wants to keep on moving. And if the object is resting, it wants to continue resting. All right, that idea of not wanting to change its motion, we call that idea inertia. So the idea that an object's moving, it wants to keep on moving, that is called inertia. And if an object is resting and it wants to not move at all and stay resting, that is called inertia as well. And the way we measure inertia is simple. The more mass an object has, the more inertia it has. And remember, the more inertia it has, that means the harder it is to actually change its state of motion. You've seen this before. Say you have a little brother and he's standing there and you push him. He's pretty light, so it's easy to push him out of the way, right? But say I was standing still next to you and I've got more mass than probably a little brother. You try to push me, I probably don't move as far because I have more mass Therefore, I have more inertia. And if I have more inertia, it's harder to change my motion. So if my state of motion was resting, not moving, it's harder to get me to move because I have more mass. Now we can take soccer, for instance. If the soccer ball is sitting on the ground at rest, it's going to stay at rest unless something acts on it. Now the wind could blow the ball. That could be an unbalanced force, right? Your foot kicking the soccer ball could be an unbalanced force. And once you kick it, that object, once in motion, will want to continue in motion. And technically, it'll want to stay at the same speed and same direction. So you might be asking yourself, well, wait, when I kick a soccer ball, why doesn't it stay at the same speed and not a straight line? Obviously, when you kick a soccer ball, it curves sometimes. Don't forget that there's unbalanced forces acting against it. And usually the big one is air. When you kick the ball against the air, right, that's the atmosphere, that's an unbalanced force. That instead of that soccer ball going in a straight line at a constant speed, it might arc a little bit. In fact, for those of you who are good at soccer, you probably know how to properly kick the soccer ball so that it angles and arcs in a certain way to give you a better chance of making that goal and scoring past the keeper. But anyways, that ball in motion wants to stay in motion until that unbalanced force stops it or changes its direction. And your hope, of course, is the back of the net so you can score that goal. All right, we know that inertia means that an object doesn't want to change its state of motion. So what if we put on top of my head a stack of textbooks, and then I had one of you take a big hammer and whack, hit that stack of books on top of my head? Do you think that would hurt my head? For first, some of you might think, yeah, that would be bad, all those textbooks, and then you hit a hammer. But remember, the books are not in motion, and they're heavy, they're massive. So when we hit those massive books with a hammer, they don't want to move. So even though you put all that force and energy into hammering those books, by the time you spread all that force out across all those books, they barely push down on my head and hurt me. You could also do this with a stack of textbooks and your hand underneath it, and then smash it with a hammer on top of the textbooks. You'll notice that it won't affect you in a big way because those books weren't in motion. They don't want to move because of their inertia. So any movement they do have, that slight change in motion, it's hard to do. It takes a lot of force because the books are so massive. And remember, the more massive you are, the more inertia you have. So let's come back to that first picture again from our unit. The idea that if you were in a semi-truck and you were moving, that rock inside of there wanted to move too, and that was its state of motion. They were both moving. Then you slam on the brakes and screech your tires and the truck stops. But don't forget that this stone is extremely massive and it doesn't want to change its state of motion. So when you slam on the brakes, the rock still wants to move forward and it ends up smashing through the truck if it's not properly strapped down. So you could see how, because of inertia, this could happen. How about if you're on an airplane and you flip a coin in the air? You're moving at about 500 miles per hour in an airplane sometimes, between 300 and 500 miles per hour, let's say. When you flick that coin up in the air, why does it fall straight back down into your lap? If you were going 500 miles per hour and you threw that coin up, wouldn't you think it would fly to the back of the airplane? Well, the reason is inertia. The fact that that coin is moving forward just as fast as your body is and just as fast as that airplane is. So your body and the coin and the plane are used to that. So when you throw it up in the air, it comes right back down in your lap because you guys are all moving forward at the same speed. That's because of inertia. Here are plenty more examples of where you've experienced inertia, whether getting lightheaded in an elevator, whether it was trying to put the head of a hammer back on by tapping it against the ground. Think about how if you've ever used ketchup, you try to shake and stop the bottle quick so the ketchup falls towards the bottom. Or think about how you have headrests that when you accelerate quickly in a car, what your head does and how the headrest blocks it from flying backwards. In fact, pause this and read through these and think about all the examples of how inertia affects you. It's something we don't pay attention to, but is all around us. So we talked about Newton's first law and inertia. The last thing we want to talk about is momentum. And momentum is specifically the inertia for a moving object. In fact, momentum's variable is a p, strangely enough. So p stands for momentum, and the way we measure momentum is the object's mass times its velocity. Now, because velocity is a vector quantity, momentum is a vector quantity as well, meaning that it has direction. But the formula for momentum is very simple. Momentum is just equal to the mass of the object, which measures its inertia, times its velocity. So as long as you know its mass and velocity multiplied together, that will give you the object's momentum. Now, an object that has momentum always has inertia because anything that has mass has inertia. But something that has inertia doesn't necessarily have momentum. You have to have velocity. You have to be moving in order to have momentum. So keep that in mind. Our last slide here gives an example how momentum can be big in different ways. Say you have a bus. This bus has a lot of mass, even though it might have a little velocity and not move fast. Because its mass is so big, it has a lot of momentum. What about an object that's really tiny? Let's say a bullet. It doesn't have much mass, but it moves so fast that it still has a large amount of momentum, right? It's hard to stop a bullet. If you put your hand in front of it, it wouldn't go well to catch a bullet. It would go right through your hand. That's because a bullet has so much momentum. And the reason it does is because its velocity is so large, even though its mass is so small. And then the last thing to think about is an object like an elephant. Say it's not moving. Even though it has a huge amount of mass, if it's not moving, it has no momentum. Because if there's no velocity, that means it's not moving. It's moving at 0 meters per second. And remember, if momentum is the mass times velocity, any mass times 0 is going to give you 0 momentum. So remember, moving objects have both inertia and momentum, but an object that's at rest only has inertia. All right? Hopefully this explains a little bit more, but this all relates to Newton's first law. An object in motion wants to stay in motion. An object at rest wants to stay at rest. And we call that phenomenon inertia, the fact that it doesn't want to change its state of motion. And inertia, if you're moving, we like to call that momentum as well. And momentum is just mass times velocity of the object. All right, science fam, thanks for listening. Let's grind even further into this and get to the bottom of understanding these concepts.